Hello, welcome back to today's class. Today I'd like to talk about probabilistic roadmaps. These are the class objectives. I wish that at the end of this video, lecture video, I wish that you can understand the probabilistic roadmap, PRM techniques, which is actually useful for handling multi-queries. As we hear, in each query comes with a start and goal position, and we need to compute the path between the start and goal. And also the last time we talked about the proximity queries, including collision detection and distance computation, which are very commonly used for any kind of motion planning technique. So basically, so far we talked about many different these classical motion planning techniques, but those techniques actually had a high running time, the long running time. In general, running time increased exponentially with the dimension of the C space. So basically, if your robot has a high degree of DOF of the C space, then basically the running time of your approach motion planning of techniques is actually increased exponentially. So it takes a lot of time. So for example, say in the D-dimension case with the grid with the 10 grid point on each dimension, then basically there are so many of these grid points. Then if you basically based on that grid point, we need to consider we can create a very large these graphs. Then there could be a lot of edges, so then it takes a lot of time even to run the simple algorithm like A-star algorithm. So there early on, basically there a lot of techniques try to come up with these motion planning techniques that exactly compute the solution, but they actually they comes with these issues of the very high running time as a function of DOF of C space. So it turns out that there are a lot of the several variants of the path planning problem turn out to be the XP space hard, which is actually show that basically it requires exponential time complexity to compute the exact solution. So let me remind you, basically ideally we want to have the complete solution, but it turns out it's actually very slow. You might recall that complete algorithm find the path if one exists and report the otherwise. Basically, if there's no solution, we need to report that we cannot have solution. One of the examples is that actually I talked about the silhouette method, this Canis roadmap technique. Also, I talked about some other also they talked about the visibility techniques. Those are the examples of some of the complete algorithm. On the other hand, on the other extreme, we can think about a heuristic algorithm like a potential field. It might have issues of the local minima, but actually we can compute their path in a reasonable amount of time. But you can see that this is unreal. Basically, it doesn't have this nice feature of this completeness property. So sometimes it may not find the path even though there's actually there exists the path. So given this trade-off issue, the accuracy, the completeness, accuracy of the computing path, also this fast running performance. Another alternative comes to another alternative technique that arise naturally. That's why there is a technique called the probabilistic completeness property. Probabilistic completeness. Basically, its main idea is that if there's solution path, then the algorithm will find the path with a high probability. So, and then if we allocate more time, then basically this technique increase the probability to find the solution. So in other words, if we allocate more time, basically we are getting higher probability to find the path. So that's actually known as this probabilistic completeness. So basically, instead of having the exact completeness property, we actually we move on to the probabilistic completeness property, and some of the recent techniques, some of the practically usable techniques comes with this property, probabilistic completeness. So here, let me illustrate one of the very common the technique, the probabilistic roadmap. Some people call the PRM, which is mainly designed for multiple coverage of the solving the path between the multiple start and goal positions. Usually that basically this technique usually assumes that the static environment. And then basically the probabilistic roadmap PRM technique satisfying this probability completeness. So this actually our C space, and this actually free, there's no collision, and this obstacle space. So here we might have collision. Here we randomly generate, somehow we generate samples in the C space. Then we might generate samples under the obstacle space or even the free space, right? If the samples turn out to be in the obstacle space, in other words, we have the collision again between the sample and then the obstacle of the environment. We cannot have that one, right? We cannot have that one in the computer path, so we reject them. But if the sum of samples turn out to be there in the free space, then there's a potential that we can utilize that sample for computing paths, right? And then we treat that as a milestone, and then we put these samples milestone into the graph. So here the graph we call it the probabilistic roadmap graph. And then suppose that these are actually milestones that are in the free space, and then we see that whether given this node, we identify this nearby node, and then we check that along the straight line path between this node, that node, and we check that we may not have any collision on the straight line. For that, we can use the collision detection technique, or we can use the link operator that we talked about before. But anyway, given these randomly generated samples and check that, and then we compute a milestone that are in the free space, and then we also check the local path between this node, and then if the local paths turn out to be there in the free space, we can use it. We put them as a local path as edge in the graph. If we do that, then basically we virtually create this kind of the graph that we can wander the A-star algorithm or some other search algorithm onto the graph. Typically, here this graph, also known as we call it the probabilistic roadmap. Basically, this graph is nothing but roadmap. But here, this roadmap graph is computed in a probabilistic way by randomly generating samples. That's the main idea. And then at the query time, we can actually have one query that comes with the start and goal. And then for the start position, we need to find the path. We connect it with one of the node in the graph that actually has the small distance. Then probably we can connect this one to there. Also with the similar operation, we connect it to the one of the node in the graph. We might connect it to here to there. In other words, we can actually we can walk from here to there, right? And then we can run the XR algorithm to connect it from here to there to find the path. Then basically, if we do that, we can find this kind of path. So basically, suppose that given the available time budget, maybe 1 second, we can generate samples and we can make this kind of local. We can make this local path and we compute this graph and make a path, right? And then if we are given with more computing time, we can generate more path. We can generate more additional graph in the probabilistic setting. Then if we do that, we can gradually expand this roadmap, and then we can actually we can capture the more passes in the graph. Then that way we can actually increase the probability of computing the path. That's the main idea of the probabilistic roadmap. And then here I showed the one way of computing the path with the one query. But once you compute this probabilistic roadmap, you can try it out on many other queries that comes with a different start and goal position. That's why the PRM techniques mainly designed for addressing these multiple queries. So again, this technique assumes the static environment. Why? So basically, if the sum of the environment changing, then you need basically this computed graph may not be valid, right? Then you need to reject all of them. You need to recompute the graph, right? Which takes a lot of time. So that's why typical PRM technique assumes the static obstacles, and then given in this environment, we computed the probabilistic roadmap. Then multiple queries can be processed in the same environment using the same PRM, this probabilistic roadmap. And then basically there are a lot of cases that satisfy these kinds of assumptions. One example is that we can ask robot to move around in a steady environment. Also, there are a lot in the industrial factory. basically we can put the robot manipulate arm in the work cell over there, right? And then in that cases, actually there are a lot of these devices, also some other working environments actually static, so that we can compute the PRM, and then we can utilize the PRM at the cases. So in general, I talked about this how we can compute how we can perform the PRM. Basically, it has two phases. First phase is that we need to do the pre-computation. In other words, we compute the roadmap construction. So here I gave you I mentioned that we can generate the sample in a random way. So we can use the uniform sampling, but we can also do many other sampling techniques, right? Basically, performance varies a lot depending on your chosen sampling technique. Later on, I will give you the very simple resampling technique doing based on this concept known as this expansion. And that once we computed the roadmap, and then at one time, once we are given the query, then we can do this query processing. In other words, we can find the path. This is actually the pseudocode of the computing the PRM, this probabilistic roadmap graph based on this uniform sampling. So basically, we start with the empty graph G with the empty vertices in H here, and then we repeat this process until we spend all the available time budget, and then we generate random samples here, the Q, and then we need to check whether we call it clear to check whether this Q is in the collision-free state. If basically there's no collision there, then we add the Q, the random sample Q, into the vertex set of the graph of the roadmap, and then we identify this nearby node by calling the nearest neighbor search, which is based on the technique that I talked about with this distance computation. So then we can compute a set of nodes in the V that are close to given the configuration Q, and then we look at then we consider node in the nearby node in this set is nearby node, and then we check whether there is this collision-free path. Here we identify the nearby node. In this case, these two nodes may be identified, and then we check whether there is basically we can create this collision-free local path. So to do that, we can call the link operator between Q and Q prime, and then there's no collision. We can add the edge between them. We keep doing that, and then again this computed graph G, known as this probabilistic roadmap. And the node, actually the node in the graph was called as this milestone, feature in this C-free space. But if you don't have many samples, actually, we might have this kind of roadmap. As you can see, there are many small disconnected the graphs, right? So basically, there one subgraph, another subgraph, and then out of them, it's very difficult to compute the path from here to there, right? So basically, if we don't have the many samples, also there are very narrow passage, then based on simple technique, generate random samples and then computing this local path among this node, then we might not able to generate this well-connected graph. At that cases, probably one simple solution is we spend more time generate more samples, and then that way we can actually we can connect the graph. But another technique is that we can somehow we can identify the very difficult region. For example, here, basically we can generate random samples. For example, this one. Then basically we try to connect it from here to there, right? But since there are very narrow passage in the C-free space, we may not able to connect it. We may not able to connect from here to there, right? Then we might have a lot of the failure cases over there in terms of connecting this node to other node, right? So then, if we can actually identify the very difficult region, then we might need to have another sampling techniques. So to do that, we measure this failure rate. Here I'm showing the very simple case of the resampling, and then basically this one is that we measuring the failure rate, and then for each node, we actually measure the number of the link operator that we try to call given the node. there, and then we also measure how many link operator actually failed. So for example, for that node, basically we might not have the many failure, but for that node we might have a lot of failure. Then based on that, we do some sort of based on this failure rate, somehow there could be a lot of nodes, so we do the normalize it right here. We normalize each failure rate for each node with the summation of the node, and then based on this one, we assign the resampling probability as a function of the normalized weight. In other words, we try out the more probability to do the resampling on the difficult region, right? And then for that region, basically we can also given this small region, and then we can do some sort of uniform sampling. But another idea might be is that for that difficult region, we do some sort of shooting. So for example, instead of generate random sample and try to connect it, we already know that it's a very difficult region, right? So instead of that, we can actually pick a random direction. We walk along that direction. If we hit the collision there, we actually randomly changing direction, and we keep doing that, right? And then at that point, we generate another node there. Then we do that here. We generate another node. We know that actually we can connect it from here to there, right? By that process, walking, and if you're hitting the wall, you change random direction and so on, right? I call it the shooting operator or the walking operator. And then we wish that basically by doing this operator, you might be getting out of this very difficult region, and then for there you also identify nearby node and then try to connect it. Then this is one simple way of the resampling by expanding the graph, right? There could be the many other way of the computing the roadmap better, even though you have a very difficult environment. One of the main issue of this PRM technique is that we need to show the probabilistic completeness, in a mathematical way. So in other words, we need to measure the error of our chosen this PRM technique. In other words, basically, if the path is returned, the answer is always correct, right? We know that. But if we are not able to find the path, then the answer may or may not be correct, right? Overall, we hope that answer is correct with a higher probability, right? Then basically any PRM technique should prove what's your probability of having the correct solutions, right? So here I'm not going to talk about the details about the proving error of the chosen the PRM technique, since it's very tedious. It requires a lot of mathematical derivations. If you are interested, I recommend you to refer to the theoretical analysis of my draft, where I showed one cases of the theoretical analysis of the simple PRM technique. But the main idea is that basically probability of being incorrect of your solution is that, in other words, as you actually here the capital N is the number of samples. In other words, as you are getting more samples, basically this is getting bigger and this is getting bigger, and in other words, here we have actually minus with the exponent is function. In other words, as you are getting more samples, basically this value is getting down and down. In other words, the error of being incorrect getting down and down. And also there are many other factors. The path. So basically L is the path length, and also the dimension. So also the R is the clearance between the robot and obstacles. Obviously, when the clear runs getting smaller and smaller, in other words, basically as you are getting the more narrow passage regions, there are small region only the free space, and that's why your probability getting bigger and so on. And also as your path length getting bigger and bigger, L is become bigger, and then basically your probability of being failure, basically that error can be bounded by higher value. In other words, you might get a high probability of being incorrect. Also, another important factor is D is that basically D is located here. Also, there it looks a little complicated, but generally, as your dimension is getting higher and higher, basically the probability of the getting incorrect solution is getting higher and higher. So basically, these are the main factor governing the probability of being incorrect or the being correct. If you are interested, I recommend you to look at this theoretical analysis of my book. Also, once you compute paths in the PRM, there may not be many nodes, right? So as because of that, actually, your path may be your path may not be very smooth. Also, it has many these kinds of turns or this kind of edges, right? And then it might be it may not be the good path for robot to track this path, right? So typically, once you compute the path, then you can do this. You need to smooth out this path. One simple solution is that given the start and goal, you pick the middle point in the path. Let's say this one, and then you check this segment from the start and the middle point. And then if there's nothing there, if there's no collision, then you can use this path instead of this very zigzag pattern. And then you do the same thing for there. Then you have collision. Then you can use this one. And then for that segment, you also you identify the middle point, this one, and then you check this one in a recursive way. No collision, no collision. Then you can use this path. So this is one simple way of smoothing the path actually. But some other recent technique is that you do this kind of the smoothing operation while you're computing the path, basically. Yeah. But here, this actually I give the very simple way of smoothing the path as this post-processing step. Once you compute the path and then you smooth out the path and you pass that the smoothing path to the robot. And there could be the many desampling strategy. I'm not going to talk about the details about this technique, but here one of two well-known techniques is actually visibility-based approach, visibility-based PRM technique for path planning. Also, there's a technique known as the Gaussian sampling strategy. Its main idea is that if we're just using the random samples, then we might basically there's this empty space. This is the obstacle. This is actually free space, the same environment, free space, and we have the very narrow passage, right? But if you're just using the uniform sampling, then to find the path from here to there, passing through the uniform sampling, we need to generate a lot of samples, right? Then we might generate a lot of the unnecessary point even in this wide empty area, right? Instead of that, it might be better to generate samples only the boundary of the obstacles. That's why actually they talked about a way of technique that generates samples near the boundary of C space, so that actually they can find the path better with this narrow passage. Also, in a similar way, visibility technique is that in this case actually there are wide empty area, and then if you are also using uniform sampling, you might need to generate a lot of samples. But if, for example, if this sample can see this sample, in other words, if you can see from here, we can see this sample here. If you can see this sample from there, it means that we can find the path from here to there, right? Without having any collision, right? It means that there's no need to have that particular node in there. There's no need to have this kind of many visible samples each other in the graph. Instead of that, we can actually have only a few samples in the wide empty area. So basically, we do that based on the visibility operator. So here I give the high-level idea of the generating sample on the boundary. Let me briefly touch a little bit more on this visibility-based approach. So again, this visibility-based technique is the classical technique. We might generate a lot of random samples, even though we have the actual wide empty area. But this end result of the visibility roadmap, you can see it's very compact. Its main idea is that we utilize concept of the visibility domain. It means that at this given configuration, we see that what are the visible domain. This is actually optical, and then somehow we compute the visibility, basically this visibility domain. In other words, in that domain, we can see there any point in the domain from here, right? So basically, this is actually the computed visibility domain. Of course, computing this visibility domain requires a lot of computation, but by now, let's assume that we can compute this visibility domain. And then for that node, we can compute the visibility domain, and then you can generate another random samples. maybe that sample is here in the visibility domain, then we cancel it. In other words, since we can see that node from here, we don't need to have that node, that node in the graph. We cancel it, and then if we generate another random samples here, out of this visibility domain here, then basically, in other words, we cannot see that node from there. In other words, we cannot connect from here to there, right? So we generate that node. In other words, we generate that node and then add that node into the graph, the PRM graph, and then we keep doing that. And then here actually we have 3 nodes, one node, another node, another node. But basically, we generate those nodes since we cannot see each other. In other words, we cannot connect from here to there, right? So in order to connect those nodes, we generate another node now known as this guard node. So for here, for this node we cannot see each other, but for that this is actually visibility region from here, another visibility domain here. Then for that region is that we can see each other. Basically in that region we can see these 2 nodes, right? So basically, if we can generate node within that region, we can actually connect these 2 nodes by passing this node, this guard node, right? So basically, based on that, we generate the guard node, keep doing that, and then based on that, we can compute this very compact world map by utilizing this concept of this visibility. That is we only identify the visible node. We cancel any other visible node within this domain. We create this invisible node, this node that we can connect it, and then later on we generate guard node that can connect it this different region. That way we can compute if you are using the uniform sampling, we might have the very dense world map. But if you are using this kind of the visibility concept, you can have very compact the graph. Obviously, it might take a lot of time to compute this world map, but once you compute it, then you have a very compact the world map at the query time. Basically, you can compute the path in a very fast way. That's the main benefit of using this technique. As you can see, there's trade-off between high cost of computing the world map, and then also how many iterations do we need to have to capture full connectivity. It depends on your underlying geometry, right? If there are a lot of the triangle, a lot of points, a lot of this information in the environment, you might have a lot of iteration, a lot of time to compute that graph, right? Also, also it turns out that the problem of capturing the narrow passage. So basically, when you have the narrow passage, you cannot see each other. You cannot see from here to there, right? Because of their very narrow free space, right? And then you need to generate a lot of samples. And it turns out that problem of capturing narrow passage is actually same to actually the one in the base PRM. In other words, even though we utilize this concept, it doesn't have that much under the narrow passage. That's why there has been the dedicated techniques handling this kind of narrow passage. But anyway, there are a lot of issues. So basically, because of that, there are many variants of PRM techniques. But depending on the task that you need to satisfy, you can choose the PRM techniques. So far I talked about the basic concept of the probability world map. Mainly I talked about the simple technique with the uniform sampling. Also, I talked about the resampling. Also, I talked about some of the very complicated technique utilizing this visibility domain. And next time I talk about another this probabilistic completeness technique known as the RRT technique, and some other recent techniques. This is the common homework. Submit the summary of the 2 recent papers from the robotics conference and journal. Go over the next lecture slide and come up with the 3 questions before the midterm exam. If you haven't done that, please, I recommend you to come up with this question soon. That's it. Thanks so much. Bye.